All right, it is a pleasure to be talking to you through the digital wonder waves. Today is sort of our big culminating day, our final day of notes on probability, and the subject that we will be messing with is conditional probability. So you will remember that the two main kinds of probability are having to do with independence and dependence. And dependence is one of the keys for conditional probability, right? We're looking at situations where one probability is dependent on another probability, and that changes the way we mess with different probability calculations. Now, as this lesson or this video goes on, things get slightly more complicated, culminating in sort of the hardest thing we do in probability. You may remember from class that by the end, you probably wrote things down and were like, I am not quite sure what's going on. So I hope that it is sinking in, and that when we return and you're looking at this lesson now, you're in a headspace to be like, all right, we're going to rock and roll. Because with probability, it is often a practice of just going through it until you fully feel connected to it. Okay. Let us roll forward. If we take a look, you should be looking alongside with your slides, and I'm on slide number 8 right now. And on slide 8, we're talking about this concept of probability of B given A. So P of B, and then there's this line and an A, and that means the probability of B, oh my goodness, given event A. And what that means is, whatever event A is, it is definite. It has happened. And now I want to know what the probability is of B occurring, given that A has occurred. The equation for this, as it says in your slides, is the probability of A and B divided by the probability of A. And the reason why the probability of A is on the denominator is because we always make the denominator and probability our like total set of values. And in a world where A has definitely occurred, the probability of A will always be the total. Probability of B and A, or A and B, will always be provided. It's either going to be provided in the data, or it's just going to be offered up as a percent. And the reason these things must be true is if our probabilities are dependent, we don't know in what way, and so we don't know the intersection between A and B unless it's given. All right, so not too terrible, right? So an example that I give you on slide 9 is this concept of probability of 4 given that you have rolled an even number. Now, I did not tell you the overlap between 4 and even, but that's because you should know this already, that the probability of a number being 4 and it being an even number is actually just the same as the probability of 4, right? So that's a situation where there's a full overlap. If you get a 4, it must be even. And so one thing to be aware of with probability is there are things that just rationally make sense. You have to look at things and evaluate them and go, okay, that is a sensible conclusion. So this is going to look like the probability of something being 4 and even, just like it says above, divided by the probability of it just being even. And if we move forward, of course, that comes out to 1/3. And the reason that comes out to 1/3 is the probability on top of it being 4 and even, right, is 1 out of 6, right? There's a 1 in 6 chance that it would be 4 and even. Why? Because there's a 1 in 6 chance that it would be 4. And if it's 4, it's necessarily even. And we are dividing that by the probability that it's even, which is a 50-50, right? Because there are 6 possible rolls you can get on a die, and half of those are even numbers, 2, 4, and 6, right? Now you can either do 1 divided by 6, and then 1 divided by 2, and then do that number divided by the second number, right? Or you can just do what I like to do, which is, in this case, just multiply by the reciprocal, right? And that gives us 2 over 6, which is equal to 1 over 3. But you can also stick this in your calculator and do 1 over 6, and then do 1 over 2, and then take whatever you got from 1 over 6, divide it by 1 over 2, which is 0.5, and you will get your value. And that gives you 1/3. And that makes good sense. If you take a look on slide 11, you see that one option is available out of the conceivable options you would imagine, given that, of course, it's even. The 4 is available, but because it's even, your sample space is not all 6 die rolls. It is 2, 4, and 6, so that's why it's a 1 in 3 chance. Okay, that should feel pretty sensible. If it doesn't feel sensible, come find me, come shoot me a remind. I got you covered. I will give you more detail. Let's move ever forward, okay? We're looking at slide 12 here. We still have the same probability of B given A, But now let's mix it up. Actually, I'm going to throw some red in here. Let's do some red. It says the probability of being an American smoker is 0.19. Now, when I map out a problem, I like to set this up, okay? So I'm going to call the probability of being an American smoker probability of A. Sorry, I was blowing hair off that fell on my screen. So probability of A equals prob of being a smoker. Okay? And we'll say probability of B is the probability of lung cancer. I was just thinking about the fact that our first one was die rolls and this one is cancer. It's like, oh my gosh, that Mr. Macy's raising the stakes over here. Okay. Now, the question says, in the question, it says the probability of being a smoker and developing lung cancer is 0.03. So we actually already know the probability of being a smoker and developing lung cancer is provided to us, right? It's 0.03. And that's the probability of A and B. Okay. So we're already on a roll. We've been given our situation. Now, when we're given the probability of A and B, we're probably already thinking that this is a dependent or conditional probability, because why else would they give us the value? If they didn't need to give us the value, right, that would be because the events are independent, and we could just multiply probability of A by probability of B. That's normally what probability of A and B is. But because they're dependent, there is an overlap, and thus that will not be the case. This question says, what is the probability of developing lung cancer given that you smoke? So you are a smoker. So this is the probability of B, probability that you have developed lung cancer, given A, the fact that you smoke. I could have assigned any letter values to either of those probabilities, but wonderfully it works out, okay? So the probability of B given A should be equal to the probability of A and B, divided, of course, by the probability of A, and so easy peasy, lemon squeezy, if that expression still holds, it'll be 0.03. You'll notice the probability of being a smoker, I probably should have written down, is 0.19, and the probability of developing lung cancer is 0.07, right? So we will divide 0.03 by 0.19 because that is the probability of A, right? Ooh, let me do a highlighter. I love the highlighter. We'll do green. That is the probability of A, right? And we will just run that calculation, and that will give us our answer. So I'm going to run it very quickly. Plug it into my calculator, 0.03 divided by 0.19, and that gives us a value, a final value, of 0.1578, so I'll say 158, okay? And that is our probability. Value found, answer achieved, etc. Okay? So that is the probability. I hope that makes sense. Be aware that, of course, we've been given these values, and it's a pretty simple process, all things considered. Make sure it feels simple. Make sure it feels intuitive. Okay, and we can see on the next slide that I have walked you through that value once again. Hopefully that makes good sense to you. Let's roll on forward to number 14, if you would. Number 14 is about peanut butter and jelly. You might remember this one from class as well, okay? Suppose that 80% of people like peanut butter. So I'm going to say probability of A, right, is going to be equal to probability of liking peanut butter. And probability of B is going to be the probability of liking jelly. Okay. And then, of course, there's probability of A and B. So let's throw our values in. The probability of A, which is liking peanut butter, is 80%. We turn that into a decimal, 0.8. Probability of liking jelly, we turn that into a decimal from a percentage. That's equal to 0.89. And the probability of liking both is given to us wonderfully, 0.78, or 78%. Okay, we have our probabilities. We should know right now that we're probably going to be doing a conditional statement, and it says, given that a randomly sampled person likes peanut butter. So given that peanut butter is liked, I already know that's on the right side of my and symbol, right? Given A, we like peanut butter, what's the probability he also likes jelly, right? Well, we're going to run our same thing. What's the probability of A and B? And we're going to divide that by the probability of A. Okay, always in this order. If they were flip-flopped, if it was the probability of A given B, then we would divide by the probability of B. But in this case, it's not. Probability of A and B, as we saw, is 0.78, and we are just dividing that by the probability of A, which we see as 0.8, so 0.8, and that gives us 0.975, okay? And that would be the probability that you like jelly, given that you like peanut butter, right? So those odds are pretty high. It should make good sense. And of course, as always, if it doesn't, do let me know how I can help. All right, we've gone through sort of the first stage, if you will, of conditional probability, and now we're rolling forward. We're on slide 15, and we're asking ourselves a new question, right? We're saying, well, how do I check for independence, right? Because so far, Mr. Mays said with love, you've basically just said if I give you the overlapping probabilities, it's likely that they're dependent, because why else would I have to give it to you? Otherwise, you would just multiply probability of A times probability of B. And that's a fair way to think about it, but I want you guys to have the actual sensibilities that get us there, right? So there are two ways, and you'll see these both listed on slide 15, but I just want to walk you through each one of them. Way one that you can check for independence is, does the probability of B given A just equal the probability of B? And again, you guys are rational thinkers. You guys know how to work on your toes. This is a beautiful thing. What we're saying here is, if the probability of B happening, given that A is true, ends up being the exact same as the probability of B happening, period, then this must be independent. Why? Because A existing, the fact that A occurred, oh, no, it erased. Why would you do that? Okay, the fact, well, actually, it was very cool, because actually erasing it proves the point, doesn't it? If the fact that A occurred doesn't change anything, then by nature, it's as if A did not impact B at all. It was Thanos snapped out of existence. All right, I'm sorry, that's a bad reference. It's a silly one. Outdated, too, my goodness. Especially for such a high-budget movie. Either way, what it shows is that the probability of A, or the fact that A has occurred, doesn't even mess with the probability of B, right? So that would show independence, right? Normally, the occurrence of another probability or of another case impacting a particular probability is what makes dependence. All right, let's take a look at 2. The other way that we can check for independence is the probability of A intersection B equaling probability of A times probability of B. Okay, I'm doing a star for times. I could obviously do an X or whatever you want, but either way, that should make good sense. Actually, let me do brackets. I feel like that's a little more sensible here. Probability of A times probability of B. And this should make good sense. This is what we were saying in the slides before and in the first video lecture, right? If there is an intersection between A and B, the way I should get that, if it's independent specifically, is by multiplying the probability of A times the probability of B. So if my question gives me a value for the probability of A and B, and it does not equal probability of A times probability of B, that means it must necessarily be dependent. So really quickly, I'm going to be taking a look at slide 16, and on slide 16, we return to our smoker problem. So I'm going to go over to my smoker problem here, and I'm going to do a little bit of work on the sides. And it says try method 1, and then try method 2 for looking at conditional probability, right? Method 1, as we saw, was the probability of B, given that A occurred, should just be equal to the probability of B. Well, let's take a look. The probability of B we have right here. It is 0.89, right? That's just the probability of B, 0.89. And fortunately, we have calculated the probability of B given A, and it comes out to 0.975. And lo and behold, this does not work. One does not equal the other. Therefore, it is not independent. It is dependent. Now, if one of these doesn't work, the other one also will not work. I will spoil it for you, but let's check it all the same. Let's take a look at method number 2. I'm going to make a line to delineate, and let's take, it's very Christmas colors there. Let's take a look at number 2. Method number 2 is the probability of A and B should equal probability of A times probability of B. Now, we know the probability of A and B. It's denoted right over here. It's 0.78. So 0.78, which is the probability of A and B, should be equal to the probability of A times the probability of B. Well, the probability of A is 0.8, and the probability of B is 0.89. I'm going to pull up my trusty calculator, and I'm going to say what is 0.8 times 0.89. And I get 0.71 as my value. And as you might guess, 0.71 is not equal to 0.78. It's just not the same. And what that tells me is that this cannot be independent. These are dependent events. All right, that should make good sense. This should all logically follow. And if it doesn't, as always, come find me. I got you covered. But let us roll forward from slide 16 onto bigger and different things. Okay. After all of this, you should feel relatively solid in everything we've done so far. But be aware, things are about to get a little more complicated. And with that scary complication comes the wonder and the heft and the brilliance of statistics and knowing that you are doing high-level, brilliant math. There are two ways that we deal with difficult visualizations, and difficult probabilities in general, I should say, is with visualizations. And the two visualizations that are the most useful are two-way tables. Once you know how to read a two-way table, it saves you a lot of calculative math. And the second one is tree diagrams. Tree diagrams simplify giant, unwieldy word problems. So moving on to slide 18, we're going to go into specifically two-way tables. You should see a two-way table in front of you, 9th grade, 10th grade, 11th grade, 12th grade, dogs, cats, and total, right? So I'm just going to go through and I'm going to start running these calculations. And what I'll notice is the first question is, what is the probability that dogs are owned by a particular grade level, right? Any grade level. But I just like calling it the probability of dogs, so I'm going to call it the probability of dogs. What you will do is you will look at that column that says dogs. You'll notice that one of the columns literally says dogs at the top, and that column just goes all the way to the end. And at the total bottom, at the bottom of that column, you have a total of 88. Now, what you need to know is that that is the total number of dogs, and you will put that on top of the total number of people surveyed, period, which is 110. That is in the bottom right corner. So you know that the probability of dogs is just 88 over 110. And that's how you read that. We know that we're looking at just the dogs probability, and we know that we're looking at it in reference to the total. Why? Because we have not set any givens, right? If no givens are set, then you just make the total probability the total number of people that have been surveyed, okay? That should make good sense. Now, the other thing, and I'm going to make a delineation here so we can see it. The other thing that they ask for is the probability of dogs given, and now we have a given, that you are in 10th grade. Now already, you should have your spidey sense tingling. And what your spidey sense should be telling you is, hey man, we have a new given, and that given is 10th grade. So we're no longer looking at the entire total anymore. We're not looking at 110. We want to look at 10th grade. So you will see a row that says 10th grade. And if you follow that row to the end, you will see a total of 20 people in the 10th grade. That is your new denominator, 20. Because it is your given statement. It is the value of the total number of things that you are actually giving credence to in this particular question, in this particular probability. Then you will make your numerator, which is the probability of dogs, again, given that you are in 10th grade. So you need to find the probability of dogs for 10th graders. And that is actually exactly to the right of 10th grade. You will see the dogs column offers you 16. And what that means is there are 16 dogs that belong to 10th graders. Therefore, the probability of having a dog when you are in the 10th grade is equal to 16 over 20. Okay, you should be able to read that. That should feel comfortable, easy, breezy, and beautiful. I then ask, are the events owning a dog and being in 10th grade independent? Show with a formula. And there's a pretty easy formula to do here. We have the probability of A, which is dogs, and we have the probability, or we could call it, we would call this actually B. And the reason I'm going to call it B is because we have probability of B given A over here. I could call it probability of A, but then it would be probability of A given B. Either way, it's the same. What you will note here is that you have the probability of dogs, and then you have the probability of dogs given a different condition. Already you should be like, wait, we already went over this concept, Mr. Mays. I know exactly what to do. I need to see if the probability of dogs given a condition is equal to just the probability of dogs. If 88 over 110, and this is so important that you understand this. Oh no, that's not what I wanted. If 88 over 110 is equal to 16 over 20, what that means is being in 10th grade, that condition does not alter the chances of me having a dog, which would make them independent. But if it does alter that, then they are not independent. They are dependent. So let's do our math. I'm going to do it right over here in this green box. Does 88 over 110 equal 16 over 20? I pull out my trusty calculator. I do 88 over 110. Hopefully you're leagues ahead of me right now. That comes out to 0.8. I then do 16 over 20, which you should also see comes out to 0.8. Therefore, they are independent. All right, that should make very good sense, both as to why that's true and as to how we went about it. Excuse me. Okay, using that same table, let's take a look at probability having to do with ninth graders now, okay? And I'm going to use this to go through the other method of figuring out if things are independent, okay? So I actually just want to put this on your radar. We've already done probability of B given A equaling the probability of B. We're now going to do the probability of B, of A intersection B, I should say, equaling probability of A times probability of B. Okay, so I just want you to know, in the wings, that's the method we're going to be using to check for independence for this next particular problem, okay? And you could do it either way, but we're going to practice both, okay? And this is the one I don't think we got to in class. And if we did get to it in class, we are awesome and legendary, but we're awesome and legendary anyway. Okay, probability of being in the ninth grade. Oh, that's supposed to say 9. There we go. Of being in the ninth grade. Okay. You look at your chart. And again, this is a great way, to check yourself and make sure we're on the right track. You should be doing this already. But I'm going to take a look. I'm looking at ninth grade. I want to see the probability of ninth grade. There are no givens in this situation. So we know that our total is going to be the total number of values, which is 110, just like with 10th grade a moment ago. The number of people in ninth grade, however, if we look at that, is coming out to 25. Okay? So we know that 25 people are in the ninth grade. The reason I say that is if you look at the row, it says ninth grade. And if you follow it all the way to the end to the total, 25 is the total presented there. And that should make good sense, so I'm going to put a box around that. That's the probability of being in ninth grade. Okay, now we want to know the probability of, once again, of cats. I love that. What's the probability of animals, plural? Okay, probability of cats. We are once again looking at the total, 110. Why? Because there are no givens. And now we want to do cats. So, once again, you are going to find cats. That is a column. You're going to scroll all the way to the end of that column, and you are going to see that the total is 22. Therefore, 22 out of 110 is the probability of cats. Okay. Now I want to see what the probability of ninth grade intersection cats is. Okay, this is really cool. You might be saying, well, wait a minute, we're going to multiply these values together. And of course we are. We're going to multiply these two values, probability of ninth grade and probability of cats, together. But we want to check it against the intersection point. I'm going to switch to green for this. Finding the intersection point of probability of ninth grade and cats is a fun little exercise. We start with the fact that we are looking for both ninth grade and cats to be the case. So if we look at ninth grade and we look at cats, we see that there are 5 cats that belong in ninth grade, right? We know that there are 5 cats that belong to ninth graders, right? And because this is an intersection, what are the odds that you have a cat if you are in ninth grade, right? We are not, and I want to make this very clear, we are not looking at any givens yet. So we are still rolling with a total of 110. Okay? So 5 over 110 should be the intersection between being a ninth grader and owning a cat, given the total number of values. Okay? Again, what are the odds that you own a cat and are in ninth grade? That intersection point. Okay, what we need to do now is we need to check the following situation. Does probability of A intersection B equal probability of A times probability of B? Well, let's take a look. That would mean that 5 over 110 was equal to the probability of A, which is probability of owning, being in ninth grade, I should say, 25 over 110, times probability of B, 22 over 110. And I'm just going to grab my calculator once again, and we are going to run this calculation. 25 divided by 110. Okay. And then we're going to do 22 divided by 110.2. And then I'm going to multiply those by each other. And lo and behold, on the right side, I get 0.04545. So I'm going to say 4, 5, and just stop it there. Then I'm going to do 5 divided by 110. And what do I get? The same value. So if I end up with the same value, given these setups, what does it mean? Well, it must mean that they are indeed independent. All right, good. Wonderful, I should say. We have shown independence in 2 cases, and in both cases that independence should be clear. Okay, we are now moving forward to slide number 19. Slide number 19, I just give you my answers for probability of dogs in 10th grade, so that's nothing new. But on slide 20, that's when the magic starts to get a little more complicated. But that's all right, we're ready for everything and anything. So let's roll ever forward. We have 3 examples here. We have 2.33, we have 2.34, and we have 2.40. We then have what I will call number 4, which is are these events independent? Now this, if memory serves, for a couple of classes, this was the struggle point where we were just writing stuff down and we weren't quite sure what went where and why, and that is totally understandable. There's a lot of information in a short period of time. So let me walk you through some of this beautiful magic. Starting with example 2.33, you will look and you will see that we have this chart for teens and parents having to do with college and college degrees. Example 2.33 says, if at least one parent of a teenager completed a college degree. Full stop. Full stop right there. I'm going to do this one in red. It says, if at least one parent of a teenager completed a college degree. So my given, therefore my denominator, is going to be everyone who has a parent of a teenager that's completed a college degree. So parents with degrees. If I take a look at that column, there is a column that says parent, and to the left it says degree. And if you go down that degree column and go to the bottom, there are 280 parents with degrees in this study. That is my given, and therefore that is my total. So if at least one parent of a teenager completed a college degree, boom, 280 is my total. What is the chance the teenager attended college right after high school? What is the chance the teenager attended college? Again, we're going to look at teen. This is a row. Teen in college. And if you follow the college one, that's the upper of the 2, all the way to the end, you have a total of 445. Okay, so that means 445 teens actually completed college, right? Okay, but this says if at least one parent completed your college degree, what is the chance a teenager attended college? So what we want there is the number of teens that completed college given the parent's degree, which is not the total of 445, but is instead 231. That's the intersection point. So you should see teen college intersecting with parent's degree at 231. And so our answer is 231 over 280. I hope that makes good sense. We are taking our total sample area that we care about, parents going to college or completing a degree, and we are putting that below as the denominator 2, chances you are a teenager given that the parents have the degree, right? aka the probability of A and B. And so that's our answer for 2.33. I hope that makes good sense to you. All right, let's pick a new color. Let's go to, let's do something new. Let's do like a purple, yeah. So now we're on 2.34. This one says, a teenager is randomly selected from the sample, and she did not attend college right after high school. Now, in one class I was talking about how there's like an oddity in the way this is phrased, but here's how we're gonna roll with this. They're randomly selected, and we know that this person did not attend college. So that's going to be our given. A teen was selected, and they did not attend college. So again, we will go to where it says teen and college in the row section, right? And we know that she did not attend college, right? So we look at the not section. And we will go to the end of that, and we will see that 347 teens did not complete college in this survey. That is our given. That is our total sample space. It is therefore our denominator. What is the probability that at least one of her parents has a college degree? We will find the intersection point between teen not and parent degree. And if you intersect those, you will see 49 teens did not go to college despite their parent having a degree. So 49 out of 347 is the total sample space we are looking for. That should make good sense. Once again, if any of it doesn't, shoot me a remind, come find me, let me know, and I got you covered. All right, let me make some separative space here. We've gone through this, we've gone through that. Now we're doing 2.40. And actually, I'll make a separator here. And let's do a new color. What am I feeling? Let's do like something in this sort of like middle. I don't know what that is. This is like a fun orange. Let's do an orange. I love orange. It's one of my favorite colors. Okay, 2.40. Write out the following statement in conditional probability notation. So already I know I'm going to be writing P of something. Probability of a random case where neither parent has a college degree if it is known that the teenager didn't attend college right after high school. I'm going to do my line because it's a given, and it says given or if it is known that the teenager didn't attend college. So I'm going to say teens not, because that's kind of how it's denoted on the table. And it says probability of a random case where neither parent has a college degree. Okay? So that's going to say parents not. So now we have probability of parents not given that teens not. Boom! That's how you would write that in probability notation. Okay? Now, the last part 4. This is the sort of a big, not frustrating one, but the one where we have to look at the table and make our full calculation. I'm going to do this one in orange too. It says, are the events teen college and parents degree independent? Well, let's look at probability of teens college. Start with that. With the knowledge that we want to know also about parents' degree. Okay, first things first. We are looking at these two things, and we want to know if they are independent. Immediately, what goes through my mind is, I'm going to do everybody's favorite. I'm going to put this actually on the side. I'm going to do probability of A intersection B should be equal to probability of A times probability of B. Okay, that's going to be my check for independence. Let's start with probability of teens college. I want you to take a moment and pause the video, find the probability of teens college, find the probability of parents' degree, multiply them, do your check for independence, and see what you got for these answers. Then I want you to check against what I'm about to tell you, so let me give you a couple seconds. All right, you should have paused the video and gotten these answers. I hope you had a good time. Hope it was a wonderful one. I hope you're like, I'm jazzed, Mr. Mays. I know I've got this one. Let's walk through it together. Let's start with the probability of teens going to college. We look at our row. Teens, college. We want the total number of teens that went to college. The total number of teens that went to college is 445. It's at the end of that row for teens college. We are putting that over the total sample space of 792. Why? Because we have no if, we have no given, okay? This is just the raw value. We'll do the same thing for parents' degree. Again, the probabilities for parents' degree, we know it's for the total. There's no if, there's no given, okay? But if we look at parents' degree and go to the bottom, we see 280 is sitting there ready for the taking. The last thing we need to do is find the probability of A intersection B. right? Again, where probability of A is teens in college and probability B is parents' degree. Probability of A intersection B would be the probability that your teen went to college and their parent has a degree, okay? So what are the odds that those two things are true? Again, this is over the total sample space of 792 because there are no given. This is just an intersection between teens going to college and parents' degree. So I'm going to start with teens going to college, right? So I'm on that row that says 231. To the right of that is 214. To the right of that is 445. But I only want the one that hits parents' degree. The only one that overlaps parents' degree is 231. Okay, so 231 over 792. So in theory, 231 over 792 should be equal to 445 over 792 times 280 over 792. So what you should have done and what I am now about to do is grab a calculator and run my calculations. 445 divided by 792, run that, okay? And then I will do times 280 divided by 792. And what I'm getting from this side of the equation is 0.199, right? 1986 or something like that. I'm going to do 199. I'm going to round to 3 decimal places here. But you can round up. You can do it 0.2. On the other hand, when I do 231 divided by 792, this side of the equation, I get 0.2916, so 292. And those do not equal one another. Therefore, these are dependent. And we already probably knew this fact just from general trivia in life, that the odds of you getting a degree go up by almost twice as much. Well, actually, by almost half as much, I should say, if you have a parent that has gotten a degree, okay? And that's how the maths out, as they say, to show us that fact. All right, this should all make sense. These two-way tables can be a mess, but go through, check through all of this, make sure it's comfortable for you, and make sure your test for independence made sense and your check for each probability made good sense on this table. You are a legend and a hero. Slide 21 just goes through reframing the equations we've already looked at in different ways. I'm not too bothered or worried about it. What I do want to do is I want to talk a little bit about tree diagrams. Be sure to read through the rules for tree diagrams. They are available on slide 22. But I want to spend my money and my time on slide 23 and slide 24. Let's start with slide 23, because in most classes I didn't actually do this one in class. We had to skip past it. So let's roll through and give it the old college try. Let's do purple for this. Now, anytime I see a confusing probability problem, I am going to run a tree diagram. Okay? Now, the problem says, consider the midterm and final for a statistics class. Oy, okay. Suppose 13% of students earned an A on the midterm. Now, already, I'm going to start my tree. My tree will have 2 branches. The reason it has 2 branches is we have a percentage of people that got a value on a midterm, and then nothing else on that, which means we have probability of A, aka a probability of A, I'm going to call it AM, which is A on a midterm, okay? So you should know that I'm saying probability of A on a midterm is probability of AM, right? Okay. And then I should also run the probability of not A on a midterm. So remember, we put that C there to say not this value, okay? So the probability of an A on a midterm was 13%. I immediately will turn that percent into a decimal. So 13% is 0.13. If the probability of an A on the midterm is 0.13, that is going to tell me that if I want the probability of not an A on the midterm, I will subtract it from 1. So that probability becomes 0.87 for the probability of not A on a midterm. Okay. And actually, I'm going to highlight those. Oh, no. There we go. I'm always like really quick to be like, oh, I'm on the highlighter, but I was not on the highlighter, forsooth. Okay. Oh, darker one. Yeah, I like that one better. Okay, so we have our 2 probabilities for the midterm. We take a deep breath. Now it says, of those students who earned an A on the midterm, so I'm looking at the top column now, the yes, okay? 47% received an A on the final. Okay, so of those that received an A on the midterm, we have a split here. We have probability of A on the final, which will be AF, right? And the probability of the A on the final was 47%, or 0.47. But, mind you, it is 47% or 0.47 of 0.13, right? Of the proportion of people who got an A on the midterm. So we're going to multiply those, 0.13. That should make logical sense to you. And I'm going to highlight that for effect, right? So probability of A on the final, given that you got an A on the midterm, is 0.47 times 0.13, okay? So they're two separate events, and we're going to multiply to get a smaller portion of those things. Okay? Now, immediately, I already know, hey, I have to find the alternative. So probability of not A on a final is going to be, instead of 47% times 0.13, it's going to be the opposing side. So 0.53, 53%, doing the same process as I did over here for probability of not an A on the midterm. And then I'm just going to do that times 0.13. Okay? And that will give me my value for that. Again, just want to highlight that to make it clear. Now we're going to do the same process. Tree that out for probability of not an A on the midterm. Because the question then says, and 11% of students who earned lower than an A on the midterm received an A on a final. Okay? So that means probability of A on the final down here is going to be, again, 0.87, because we have that value rigged up, times 11%, so 0.11. Okay, and then that means that the probability of not A on a final, given that you did not get an A on the midterm, is equal to the same 0.87. But now you're going to multiply it, instead of by 0.11, by 0.89, because that is 1 minus 0.11. Okay, all of these values should make sense, your values and their not values. Now you got your little tree set up, okay? And what the question asks is, you randomly pick up a final exam and notice that the student, we're running low on battery, and notice that the student received an A. What is the probability that this student earned an A on the midterm? Okay, we have our given. And lo and behold, what is our given? Oh, that is not what I wanted. I thought I was on the marker. Perfect. What is our given? I pick up a final and notice the student received an A. So I'm going to scroll through and look at where my kids get A's on finals. And they get it here, and they get it here. Those are the only two places where I see a probability of a student getting an A on a final. So let me run this calculation real quick, because I need to know what those values will be. What is 0.47 times 0.13? Let's find out together. So you will do 0.17. You will do 0.17 times, did I say 17? What am I doing, guys? 0.13, you're shouting it out. You're saying, Mr. Mace, get it together. Times 0.47. And that gives us 0.06. So you should get 0.06. It's like 611. I'm going to call it 0.06. Now you'll do the same calculation for this other A on the final probability, but this is for not getting an A on the midterm. And that comes out to 0.87 times 0.11. And that comes out to about 0.106 or 1067. And that's our probability there. Okay? So, scrolling back to the initial. We now have our probabilities of getting an A on the final. We need to roll. We need to be sure that this is going to work out, and we need to feel confident that these values will take us to the place that we belong. Oh, wait a minute. I accidentally typoed in. You probably got a different value here, I'm realizing. I accidentally typoed in 0.97. I knew that looked a little off. All right, 0.87. All right, what you really should have gotten is 0.0957. All right, sorry about that. Thank you, though. Okay, just because I could hear you again through the multiverse saying, Mr. Mays, rerun that calculation. I got you, Chief. I got you. All right. Those are our total number of values of people who got an A on the final. That's our sample space. So our sample space is 0.06 plus 0.0957. Okay, wait, deep breath. We made a tree diagram. We found the probability of getting an A on the midterm. We split that up into the probabilities of getting an A on a final and of not getting an A on a final, given the A on the midterm. We checked for the probability of not getting an A on the midterm by doing 1 minus the probability of getting an A on the midterm. We then split the not getting A on the midterm up into the probability of getting an A on the final and the probability of not getting an A on the final. Then we read our question and saw that they said, given that you pick a test and the student got an A on the final, and when we saw that, we knew that our denominator would be the sample space of all conditions where the student got an A on the final. So we added the probability of getting an A on the final given an A on the midterm, and the probability of getting an A on the final given not getting an A on the midterm. And we added them together to make our total sample space. It says, what is the probability that this student earned an A on the midterm? That will be our numerator. And the probability that they earned an A on the midterm, as we know, given that they earned an A on the final, is 0.06. Do not pick the probability they got an A on the midterm overall, because we know this student also got an A on the final. We pulled that, right? It is the probability of B and A. So it will be 0.06. And lo and behold, you should be getting 0.06 divided by 0.1557, etc. Yada, yada. And we will run our calculation. 0.06 divided by 0.1557. And we end up with our final assessment. 0.385. And that, my legends, is the probability that you will get an A on the midterm, or that you got an A on the midterm and thus got an A on the final, right? In other words, this is the probability the student earned an A on the midterm, given that they had an A on this final exam. Okay, deep breath. Run through that one again, re-listen to these notes, make sure that has stuck with you wonderfully. Okay. Rolling on to the final slide of our problem set here. Number 24. This one I did with you in class. It is also accompanied by number 25, which breaks down the entire tree. I would run through and redo number 24, make sure you're comfortable with it. But very quickly, let me just give us the solution for it, okay? I'm not going to read through the problem, but you should be able to read it. I'm on slide number 25 now. You see all of the setups. What I want to direct your attention to is on the mammogram side, okay? So you should see the beginning part of the tree. But on the mammogram side, we have positive, negative, and these are positive and negative given cancer. And then we have no cancer. Positive, negative. Right? And you'll notice our dependent values are always the lower branch, right? The negatives, the no's, those are the lower branches. And we run these calculations out. We see that the odds that you have a positive test result and that you have cancer, given that you have cancer there, and that you have cancer in the population of all random 40-year-old women, is just 0.00312. And the odds that you get a negative score, given that you have cancer, but also given the fact that you are in a population of random 40-year-olds, right? What are those odds? The odds are 0.00038, right? And this should make sense. A false negative on a cancer report on a random individual, and the odds of them having cancer and also getting a false negative are going to be very small. Similarly, though, or I guess conversely, the odds of not having cancer are very, very high, right? All things considered. And then we multiply that out to the odds of getting a false positive, and that gives us 0.06976. And then not having cancer and getting the accurate negative, a much higher value, 0.92675. Okay. I would go through, I would make sure that by reading the problem on slide 24 and looking at this tree diagram on 25 and referring back to the way I broke down the problem on slide 23, it should be pretty intuitive why this works. I just want to clarify. The problem asks, if we tested a random woman over 40 for breast cancer using a mammogram and the test came back positive, what is the probability the patient actually had breast cancer? So we tested a random woman. The test came back positive. She's a random woman, so we are not specifying cancer or no cancer. We do not know yet. What we do know is she's a random woman over 40, which is our sample, and we know that she has cancer. So our sample space will be 0.00312 plus 0.06976. That's our sample space. Same as what we did with slide 23. It says if we tested the woman and it came back positive, what is the probability she actually has breast cancer? So of these two positive options, only one of them is the positive option where the woman has breast cancer. And that is the one that we are going to put at the top of our equation, 0.00312. The same as what we did on the last problem. And we will run this calculation right now as we speak. We get 0.00312 plus 0.06976. I'm going to make sure I put this in right. Boom. You should be getting about 0.07 as the denominator here. The numerator is 0.00312. You will then do 0.00312 divided by 0.07-ish, right? And you will get your final answer, 0.045, we'll say. Those are the odds. This comes out to about 4.5%. But what that means is that these are the odds that if you're a random 40-year-old woman, over 40, I should say, and I test you for breast cancer, right? And it comes back positive. There is a 4.5% chance that you actually have breast cancer. All right. One more deep breath in. Okay. We have run through all of these possibilities, all of these problems. I guarantee you, I want you to know this, bottom of my heart, though this can be confusing, my goodness, you probably even remember moments in my class with you where I was flummoxing myself and you were like, Mr. Mays, you're the teacher. And what I want to admit to you is this. Probabilities, especially as we frantically work through them, have the probability, the option here, of really throwing us off course. But it's okay. Take your time. Check your bases. What we did today is we learned how to use tree diagrams 2 times over to determine probabilities. We learned how to create them, how to read them, and how to apply them. We learned all of the tenets of conditional probability, how to check for dependence and independence, how to determine and read two-way tables in all of their speculative methodologies. We then also learned how to apply those to a variety of different questions. We checked over, as we said, the independence conditions once again. We then made sure that we understood those methods and could apply them readily, and that we could find any probability we needed if asked for. We also determined that we know how to notate both the probability of an event, the probability of another event, the probability of 2 events happening, right? One and the other. The probability of that intersection, and also the probability of something happening given another thing. We finally also looked at some pretty simple data, and we were able to determine, hey, here are the odds that this happens given that this happens. Okay? This has been conditional probability with Mr. Mays. Go through this video multiple times. Know it inside out and backwards. Connect with it. Understand it. Know that I am with you virtually, pushing you on and saying you can do this. You are capable. You are brilliant. Thank you for being my student. Thank you for going on challenging adventures with me and pushing yourself as I push myself, because conveying things like probability to others, I will warn you and betray to you, can be a bit of a snitch. But I am so thankful to have such a brilliant class to share my thoughts with. You are legends. Ask me questions. Get ahead of it. I will see you as soon as conceivably possible, ready to get back to the stats grind. This has been Mr. Mays, signing off.